Hi everyone, my name is Kankana Sekia, a research scholar student in National Institute of Technology, Silchar. Today I am going to present my work, Microwave-Assisted Solketal Production by Acetalization of Glycerol, a byproduct of biodiesel production using functionalized cellulose catalyst. Here's the content of this work. Abstract, introduction, novelty of the work, objectives, Solketal production, experimental design, followed by results and discussion and concluding remarks. So this is the abstract of this work. The objective of the study was to prepare carbonaceous catalyst. So for this production of this catalyst, cellulose was taken as the starting material, and the functionalization with sulfuric acid was done using 1:10 weight by volume ratio under 1-pot hydrothermal treatment at 80 degrees Celsius for 18 hours. The synthesized catalyst was named as CSO3H. It had a large surface area of 447 meters square per gram, a pore radius of 30.02 angstrom, and a pore volume of 0.157 centimeter cube per gram. The total acidity of the catalyst was 4.56 millimole per gram, and the sulfonic acid density was 1.31 millimole per gram. It was used in acetalization of glycerol to produce Solketal under microwave irradiation. To produce maximum amount of Solketal, 4 reaction parameters were optimized, and the optimized reaction conditions were 1:5 molar ratio of glycerol and acetone, catalyst loading of 7% at 70 degrees Celsius in 10 minutes. Under the optimized conditions, the glycerol to Solketal conversion was found to be 97.1%. This catalyst showed excellent reusability, giving 82.1% conversion at the 5th reaction cycle. So this is the introduction. Now, since non-renewable energy sources are getting depleted at an alarming rate, the research on renewable energy source is very much important. Biodiesel is a renewable energy source with the potential to meet future energy demands, and it can lower greenhouse gas emissions. When biodiesel is produced using transesterification, along with biodiesel, a byproduct glycerol is formed in around 10% mass balance. Now, with this continuous expansion of biodiesel production, and excess of glycerol is predicted to accumulate, spurring research into the conversion of this crucial feedstock to high-value compounds. One such valorization product is Solketal. So glycerol can be valorized to Solketal by acetalization with acetone. When Solketal is blended with gasoline, it can improve the octane number by 2.5 points, and it can lower the gum formation. Solketal is a versatile solvent, plasticizer, anti-freezing agent, suspension agent in pharmaceutical preparation. It can act as an additive in other industries. It is also a useful fuel additive that can reduce the emissions. Here we are focusing on the carbonaceous heterogeneous catalyst. Now, heterogeneous catalyst, they have many advantages than that of homogeneous catalyst. Their advantages include ease of separation, reusability, easy handling, appealing acid-base characteristics. Many of them show hydrothermal stability, and their cost is also low. Again, some have high abundance, non-toxicity, and many other several catalytic applications can be seen. Currently, a rising interest has been seen in the synthesis of catalysts from biomass resources in recent years, which offers natural precursors with benign, economic, and eco-friendly methodologies. Hydrothermal carbonization can be done, and when hydrothermal carbonization of biomass is done, it can lead to highly stable and functionalized carbon materials. So this is the novelty of the work. For the first time, a carbonaceous catalyst from cellulose at a low temperature of 80 degrees Celsius in 18 hours was produced. It exhibited high acidity and high surface area. So the second novelty is Solketal and the microwave. So the prepared catalyst was used to produce Solketal from glycerol using microwave, and we could get 97.1% of glycerol in 10 minutes. These are the objectives of this work. So the first one is to prepare an acidic carbon catalyst from carbon source, then to use this catalyst for Solketal production, and finally, the catalyst should be able to be used in multiple reaction cycles without significant loss in activity. Here's the Solketal production schematic representation. So in the first reaction, we could see that transesterification of triglycerides are done. In this process, biodiesel is produced, but also as a byproduct, glycerol is produced. Now, this glycerol can be valorized to Solketal by treating it with acetone. This is the experimental design. So we have taken cellulose as the starting material. We have treated it with sulfuric acid at 80 degrees Celsius for 18 hours by doing hydrothermal treatment. And then we get the catalyst, and we have shown the catalyst with a representation like this. Here, the blue dots represent the sulfonic group that have come from H2SO4, and some other acidic group like OH, COH are also there that are coming from the cellulose itself. So this way we can prepare our catalyst. This is the whole synthetic procedure for Solketal. So when transesterification of oils are done, we get biodiesel. And along with this biodiesel, byproduct glycerol is formed in around 10%. When it is treated with acetone in presence of the CSO3H catalyst, we can get Solketal. Now, this Solketal can be used as a fuel additive, plasticizer, suspension agent, versatile solvent, antifreezing agent, etc. And these are the optimum reaction conditions. In the results and discussion section, we have done many analytical techniques. So first, the catalyst was analyzed with FTIR so that we can find out the different functional groups present in the catalyst. The band present at 3397, it corresponds to the stretching vibration of wedge bond. The occurrence of peaks at 1693 and 1571 are due to carbon-carbon double bond and carbon-oxygen double bond. The presence of SO3 was confirmed by the peak at 1021 centimeter inverse. The catalyst was also studied using XRD analysis. So we got a broad peak in the range 2 theta ranging from 15 to 25, which indicates that successful carbonization of cellulose has occurred. It also shows that the material is very disordered and an amorphous structure. The randomly organized SO3H, COH, and OH groups, they make the catalyst amorphous. The thermal stability of the catalyst was studied using DG analysis. So up to 68 degrees Celsius, the catalyst was stable. From 68 to 100 degrees Celsius, a mass loss of 5% was seen, and it was caused by the evaporation of moisture. After that, the catalyst was further stable till 200 degrees Celsius, beyond which a mass loss of 8% was seen in the range 200 to 300. Again, from 420 degrees Celsius, the carbonaceous material in the catalyst, they got oxidized to carbon monoxide and carbon dioxide, which resulted in a mass loss of 27% in the range 420 to 600 degrees Celsius. The catalyst was also studied using BET analysis. From BET and BGS method, the specific surface area, pore radius, and pore volume were found to be 447 meters square per gram, then 30.02 angstrom and 0.157 cc per gram. The pore radius is 30.02 angstrom, or we can say that the pore diameter is 6 nanometer, around 6 nanometer. So the material is a mesoporous material. The nitrogen adsorption-desorption curve, it displayed a type 4 isotherm, and a hysteresis characteristic loop was seen. So altogether, it means that the material is mesoporous. Also, extra photoelectron spectroscopy of the catalyst was done. The peaks at 165, 283, and 532 revealed that sulfur, carbon, and oxygen are present. Further, the carbon, oxygen, and sulfur spectrum can be deconvoluted. In the deconvolution spectrum of carbon, the peak at 283.35 was because of carbon-carbon single or carbon-carbon double bond. The peak at 288.25 was due to carbon-oxygen double bond. In the deconvolution spectrum of oxygen, the main peak at 530.05 was seen with a shoulder at 534.10, which was attributed to carbon-oxygen single bond and carbon-oxygen double bond. Peak in the range 166.3 to 167.05, it corresponds to the bonded sulfonic group. The morphology of the catalyst was studied using scanning electron microscopy, transmission electron microscopy, and the elemental composition was studied using energy dispersive X-ray spectroscopy. Now, from the same images, we could see irregular particles with less homogeneous morphology, and it was caused by the aggregation of removal of water during the hydrothermal carbonization step. From the SEM mapping images, we could see that the sample is of homogeneous composition. Further, the composition has been studied by EDS, and it shows that carbon, oxygen, and sulfur is present. Sulfur is present in 4.28%, which is equivalent to 1.31 millimole per gram of sulfonic, and it makes the catalyst highly acidic. Further, the catalyst was studied with them, and at an increasing resolution of 20 nanometer, we could see sheet-like carbonaceous framework in the TEM analysis. For the optimum production of Solketal, 4 reaction parameters were optimized, and how the conversion of glycerol changes with the parameters has been shown in these 4 figures. Figure A represents how with catalyst loading the conversion is changing. First, from 1 to 7%, the conversion increased, and when the catalyst loading is further increased, from 7 to 9, it decreased. So that way we find out that the optimum catalyst loading is 7%. Similarly, we can see the effect of other reaction parameters, and we have thus found out the optimum conditions. Catalyst loading is 77%, time is 10 minutes, temperature is 70 degrees Celsius, and the glycerol to acetone molar ratio is 1:5. We studied the kinetic of this acetalization of glycerol process. We did the kinetic study at 40 to 70 degrees Celsius. So we found out the conversions at 4, 6, 8, and 10 minutes at these 4 temperatures. And then we plotted this -1 by x versus time graph. Since acetone is present in more amount than glycerol, we assumed the reaction to follow a pseudo-first order reaction. And since we got the linear plots, that's why we can say that it is following a pseudo-first order reaction. Further, we found out the red constant K values from the first plot, and then we take the ln K value and we plotted ln K versus 1 by T. Finally, the equation that we get from this plot, we compare with Arrhenius equation, and we found out the activation energy to be 23.65 kilojoule per mole from this comparison. The product was analyzed with 1H NMR, and we are getting some characteristic peaks that shows that 5-member Solketal ring has been formed. For example, at 1.38 and 1.45, 2 singlet peaks are seen. That is because of the methyl hydrogen of the Solketal. Then a broad peak at chemical shift value of 2 is seen. That is because of the hydroxyl hydrogen. Again, in the range 4.24 to 3.59, peaks are seen, and it has a total integration of 5. Thus, it represents the CH and the CH2 groups present in the Solketal molecule. All of them have been designated as D. There is another peak at chemical shift value of 2.17, which refers to the methyl hydrogen of acetone. The product was further characterized with 13C NMR, and the characteristic peaks have been got. For example, the peak at 25.27 and 26.71, they was because of the methyl carbon of the Solketal. Again, the carbon present near the OH group, it is giving a peak at 63.01. So that way, with the literature comparison, we have found out that these are the characteristic positions for the 13C NMR, and that way we can confirm that 5-member Solketal ring have been formed. For industrial application, the reusability of a catalyst is very much important. So we have studied the reusability of our catalyst for 5 reaction cycles. So after one reaction cycle, the reaction mixture was centrifuged, it was isolated, and then it was washed with methanol and chloroform. Then we dried the catalyst at 80 degrees Celsius for 5 hours, and then we used this catalyst for the next reaction cycle. So this way we continued the step for 4 times, and we got conversions like 97.1 in the first reaction cycle, 93.3 in the second reaction cycle, and finally we got 82.1% conversion in the fifth reaction cycle. With repeated recycling of the catalyst, a mild decrease in glycerol conversion was observed. It has excellent catalytic activity and it can be reused 5 times with no almost significant activity drop. The recovered catalyst, after the fifth reuse, it was studied with same EDX, and from the same images we could see that the catalyst is showing similar morphology with the fresh catalyst. And from the EDX study, we can see that sulfur content is 3.5%, while in the fresh catalyst, sulfur content was 4.2%. So there is a small decrease in sulfur content from 4.2 to 3.51 as shown by the EDS analysis. And this decrease in sulfur content might be responsible for the decreasing catalytic activity on repeated reuse. We also studied the recovered catalyst with XRD and FTIR. After each cycle, the catalyst was recovered and its XRD and FTIR was studied. So we could see there is a similarity in the XRD and FTIR between fresh catalyst and recovered catalyst, which again proves that the catalyst is stable on repeated reuse. With this, I would like to conclude that the byproduct glycerol of biodiesel industry has been selectively converted to Solketal. Solketal can be used as a fuel additive, plasticizer, solvent in many industries. The CSO3 catalyst showed excellent activity in the conversion of glycerol to Solketal with better reaction conditions and turnover frequency than many reported heterogeneous catalysts. The high acidity of catalyst, its suitable pore size, and high surface area are the aspects that lead to higher conversion of glycerol to Solketal. The catalyst can be effectively used for multiple reaction cycles with no significant activity loss, making it a suitable candidate for industrial application. The catalyst was prepared from cellulose, which opens the door to further research on catalyst preparation from abundant lignocellulosic materials. That's all from my side. Thank you very much.